All right. In this video, we're going to take a look at how to kind of merge algebra and what you've typically done with algebra for the longest time, which is solving equations, and introducing the idea of solving equations with trigonometric functions in them. So, for example, if I asked you to tell me every x value to which the sine is equal to 1/2. And I want this only in radians. So we're only going to work with radians today when we're solving equations. Um, if I said find all of the values of x that make the equation true. Okay, so tell me every place on the unit circle where sine is equal to 1/2. Well, I know sine is equal to 1/2 at pi over 6. It's also equal to 1/2 at 11 pi over 6. Because on both of those spots on the unit circle, nope, that is wrong. It's not 11 pi over 6. It's 5 pi over 6. Because I'm looking at a sine value of, which again, this is what we're looking for right here. Essentially a y coordinate on the unit circle of 1/2. So sine is equal to 1/2 at pi over 6 and 5 pi over 6. But it is also equal to 1/2 if that angle is anything that is the same as pi over 6 or 5 pi over 6. Or meaning anything that's coterminal to pi over 6 has a sine of 1/2. So I could add or subtract 2 pi to this. So I could add 2 pi, which would be 13 pi over 6. I could subtract 2 pi and get a negative 11 pi over 6. I could add another 2 pi or subtract or keep going over and over and over. Okay, 5 pi over 6 is the same as 17 pi over 6, which is also the same as negative 7 pi over 6, which I got from subtracting 2 pi from that. Because remember, 2 pi has a denominator of 1, but you could say 2 pi over 1 is the same as 12 pi over 6. So what I'm essentially doing is adding or subtracting 12 pi to the numerator. Okay, but there is technically an infinite number of correct answers for this. But it's not all numbers, right? It's just an infinite list of very specific numbers which have a sine value of 1/2. So how I'm going to write this is I'm going to say that x could be pi over 6 plus or minus 2 pi times k, where this k value is any integer you want. It could be positive or negative 1, positive or negative 2. How many times you want to go around the circle, you can do it as long as you are coterminal to pi over 6. Okay, so this is kind of the notation that we are going to use to show that not only is pi over 6 a correct answer, but anything that is coterminal to pi over 6. So by writing it like that, coterminal to pi over 6, I've taken care of that. But what that does not include, this expression or this equation we just wrote, does not include any of these values. So what I'm going to do is I'm going to write a second statement that says x could also be 5 pi over 6, but then I'm going to use the same notation of plus or minus 2 pi k. So this is the set of, this is the solution to that equation. X could be pi over 6 plus or minus 2 pi k, or x could be 5 pi over 6 plus or minus 2 pi k. Okay. So that wasn't really a warm-up. We kind of got right into the meat of the lesson without, explain or just in the warm-up. So what we're going to do is we're just going to look at different situations where I'm going to use this idea that technically we have an infinite number of solutions. So what's the period of sine and cosine? Well, if you remember, both of those had a period of 2 pi, which is why we had plus 2 pi k here. But tangent only has a period of pi, and that's going to be important because when we're solving equations that have tangent in it, we are going to not use plus or minus 2 pi k. We're just going to use plus or minus pi k. So, all right, let's get into it. Again, these are just a series of examples that'll kind of start simple and then build their way up in difficulty. So if I asked you 2 cosine x plus 1 is equal to 0, if I was to solve this, I need to get the trig function by itself. So I'm going to go ahead and subtract 1 from both sides. I got 2 cosine x. 2 cosine x is equal to -1. I'm then going to divide by 2 on both sides, and I get cosine x is equal to -1/2. Okay. Well, now it's just like the warm-up. Tell me every spot where the cosine is equal to -1/2. Okay. And if, like, again, in a perfect world, we can do this without our unit circle. Cosine being -1/2, I'm looking at a 60-degree reference angle in quadrants 2 or 3. And these angles are, this is 2 pi over 3, and this is 4 pi over 3. Because both of those have a horizontal leg of -1/2. It's 2 pi over 3, not 2 pi over 2. So there are my two solutions. 2 pi over 3. 2 pi over 3, and x is 4 pi over 3. But again, I need anything that's technically coterminal to either one of those. So I'm going to put plus or minus 2 pi k, plus or minus 2 pi k. And that is my set of solutions. Okay. It needs to be written like that. It is not good enough to say 2 pi over 3 and 4 pi over 3. It is tell me all of the solutions to the equation, meaning tell me all of the values that the variable could be so that I could get a cosine of -1/2. So there's that first one. That's kind of like the entry level difficulty for solving these trig equations. Tan squared minus 3 is equal to 0. Okay, well, I don't know what the heck tan squared is, but let's go ahead and add that 3 to both sides. So we got tan squared of x is equal to 3. Here I'm going to have to square root to get rid of the squared, right? I can't really divide by tangent on both sides or do anything, but I can undo the squared by square rooting both sides. Here's the thing. When I am square rooting, I need to introduce plus or minus. Okay, it is not good enough to say tangent theta equals square root of 3, or not theta, but tangent x equals root 3. I have to, because anytime you are solving and you are square rooting, we have to introduce plus or minus. Okay, I'm going to make this red just to really try to reiterate that that's why we did the plus or minus. I don't like thinking of this as one big statement. What I'm going to instead do is I'm going to break this off. I'm going to say, where is tangent x equal to negative root 3, and where is tangent x equal to positive root 3? Okay. Again, I'll go back to the unit circle. Tangent is sine over cosine. So it's the y coordinate divided by the x coordinate. So that means I want root 3 over 2 on the y and 1/2 on the x. So then I'm looking at a 60-degree reference angle. So this is pi over 3, and tangent of that angle is root 3. Over here, I have 2 pi over 3, but this tangent is equal to negative root 3 because I have a negative y coordinate, or sorry, a negative x coordinate and a positive y coordinate. Down in quadrant 3 at 4 pi over 3, I have tangent is back to being positive root 3 because I have a negative divided by a negative for y and x. And then over here at 5 pi over 3, I have the tangent is back to negative root 3. So that's actually all of my angles for both equations, or for both positive and negative root 3. So here for tan x, I've got x is equal to, the first time that tangent is equal to negative root 3 is at 2 pi over 3. And then it's equal at 5 pi over 3, and then back at 2 pi over 3. And this is where I am not going to necessarily say, I don't need to say 2 pi over 3 plus 2 pi k and 5 pi over 3 plus 2 pi k. Because we are dealing with tangent, tangent has a period of pi, and that's because that these values will always occur 180 degrees or pi radians apart. So all I'm going to do to encompass both of these solutions right here, for both this quadrant and this quadrant, I can write that in one single statement by saying 2 pi over 3 plus pi k. Now, could you say 5 pi over 3 plus pi k? Absolutely. As long as you start with one of the angles that is, I'm actually not going to box that in because that's only half of our solution. The other half of the solution is pi over 3, which is the first time after 0 that the tangent's equal to root 3. And then I also have 4 pi over 3 down there. So I'm going to say x has to be pi over 3 plus pi k. And these two together create my solution set. So those are all the solutions, or all the values where the tangent is equal to root 3 or negative root 3. So there's our first exposure to tangent. Yeah, that's how we're going to write that. Go ahead, pause the video, see if you can figure out where sine x is equal to cosine x. Okay. You could do this a couple different ways, but where is sine x equal to cosine x? If you just think about, like, where are they equal, that has to be on a 45-degree reference angle. So at pi over 4, sine and cosine are the same. And then also down here at 5 pi over 4. So one thing I could do is I could say x is pi over, and that those are, sorry, quick side note, those are the only two where sine and cosine are equal. If I go to quadrant 2 or quadrant 4, sine and cosine are the same absolute value. They're both root 2 over 2, but sine is negative, cosine is positive, or vice versa. So that's why I'm not considering quadrants 2 and 4. So x is pi over 4 plus 2 pi k, and then x could also be 5 pi over 4 plus 2 pi k. This is correct, but it's not the simplest way I could write that answer. Because my two solutions are exactly pi apart, if I just keep adding pi, oops, let's write it a little bit cleaner. If I just keep adding pi, I'm just going to keep, I'll always be coterminal to one of those two angles if I just keep going 180 or halfway around the circle. So the shorthand way you could write that is, I'm going to go ahead and say just x is pi over 4 plus pi times k. So I could write it like that as a single statement, or, and I'm not going to, this is not incorrect to write it like that as two separate. It's just, again, if you were to see this in a multiple choice question or in the textbook answer key, we'll write it as pi over 4 plus pi times k. Okay, a couple more that we're going to take a look at, because now we can bring in factoring to the equation. So this equation looks ridiculous to solve. 2 cosine squared minus 7 cosine plus 3 equals 0. But effectively, what we're looking at, if I think of cosine, like in the previous examples, we've gotten the trig function by itself. It was kind of our first priority. And that is kind of treating cosine or sine as its own variable. So essentially what we're dealing with is 2x squared minus 7x plus 3 equals 0. It's just that our x or our variable is actually cosine x. So if I think of it this way, I'm going to just try to factor 2x squared minus 7x plus 3, and then go from there. With 2x squared, I know it's got to be 2x and x. 3 is a nice like C term, because I know that this number and this number have to be factors of 3. So it's got to be 3 and 1. Whatever number I put here is going to get doubled if I were to FOIL, because remember, factoring, all we're doing is reversing or undistributing. So because I want negative 7x, I'm actually going to put a minus 3 here and a minus 1 there. Just a quick check. I got 2x squared minus 6x minus 1x and plus 3. Those combine to be negative 7x, so we're good. So this is the correct factored form of 2x squared minus 7x plus 3. How does that help us? Well, all I'm going to do is, instead of seeing x here, I'm going to replace it with cosine of x, because that's effectively our variable. So this is going to become 2 cosine x minus 1 times cosine x minus 3 equals 0. Okay. And the whole reason that we factor is so that I can break it into two separate factors or binomials that independently are easier to solve, to figure out when they're equal 0. Because these are being multiplied together, I just need either cosine x minus 3 to equal 0, or I need 2 cosine x minus 1 to equal 0. You might be like, oh my gosh, I have to do this twice? Well, not really, because if I add 3 to both sides here and I get cosine x is equal to 3, if you think about what does cosine look like, it's a wave that oscillates with an amplitude of 1, and it goes between negative 1 and 1. So when is the cosine curve at a y coordinate or a y value of 3? Never. So this portion has no solutions. Like, this is impossible, which is nice, because now I can just really focus in on when does 2 cosine x minus 1 equal 0. So we're going to do what we've done and add 1 to both sides. I got 2 cosine x equals 1. Cut it in half. Of cosine x equals 1/2. Cosine x is equal to 1/2. This is the mistake I made earlier. Cosine x equaling 1/2 happens at pi over 3 in quadrant 1, and then also at 5 pi over 3 in quadrant 4. And of course, anything coterminal to either one of those angles will also have a cosine of 1/2. So I'm going to put plus or minus 2 pi k, plus or minus 2 pi k. Again, there's no solutions for the second half of my factored form, so that is my full solution set. The pi over 3 plus or minus 2 pi k, as well as 5 pi over 3 plus or minus 2 pi k. So if you see the same trig function twice, one's squared and one's not, you are probably going to have to factor. And again, if you want to go off to the side and kind of pretend like it's not cosine x, but it's just a variable, you certainly can, because that's more what we're used to factoring. All right, last one. 1 plus sine x equals 2 cosine squared of x. Now this one gets a little tricky, because not only do I have sine, but I have cosine squared. And this is different from the previous problem, because in the previous one I had I had cosine squared and cosine. So I could treat it as like x squared and x. The issue here is that this trig function and this trig function are not the same. Sine and cosine, they're different things. So I can't treat it as like 2x squared and 1x. I have to do some work. I need to have either all sines or all cosines. And that's where our formula sheet is going to come into play. I can't magically turn a sine x into cosine x. But what I can do is I can change cosine squared into something in terms of sine. Because if we look back at our formula sheet, we know that cosine squared, sorry, wrong one. We know that cosine squared is equal to 1 minus sine squared if I subtract sine squared from both sides. So I'm going to go ahead and make that swap. So this is going to become 2 times the quantity 1 minus sine squared of x. Now, if I distribute on the right side, I'm going to have 2 minus 2 sine squared. And now the only trig function I have in this equation is sine squared, or sorry, is sine. So now I can treat this like a factoring problem. And so when we factor, we need all the quantities or everything to one side. I need 0 in the equation somewhere. I personally don't like to factor when my squared term is negative. It's just like I'm not great at that. So I'm going to move everything over to the left side and make the right side equal to 0. So I'm going to add 2 sine squared of x. I'm going to add 2 sine squared of x. Then I'm going to subtract 2, which I can actually do from the positive 1. So what happens here is I have 2 sine squared of x. I'm going to put that out front. Then I have my sine of x. Then I have the 1 minus 2, which is going to give me negative 1. And that equals 0. Okay. So now, again, I can kind of treat this as 2x squared plus x minus 1. So let's go ahead and factor this. Again, it's 2x and x. Positive and negative 1 is the only way to make negative 1. Positive and negative 1. Positive 2. Okay, so positive 1, negative 1. Because then here I'll have negative 1x. Here I have positive 2x. And together they make positive 1. Okay, so we have the factored form. If you need more time to process the factoring piece, certainly take that time. I know some people learn factoring different ways. I used to teach it a different way, factoring by grouping is a method that a lot of people, or the AC method, whatever you need to do. Anyway, going back to this, what I can do then is use what I just did to factor this equation into 2 sine x minus 1 and sine x plus 1. So now if I take a look at this, I've got 2 sine x minus 1 has to equal 0, or I need sine x plus 1 to equal 0. Well, this is going to simplify to sine x has to equal negative 1, and this is going to simplify into sine x has to equal positive 1/2. We've actually already seen the sine of x equal 1/2. That happened at, I messed this up once, so I'm not going to do it again. That happened at pi over 6 and 5 pi over 6, plus or minus 2 pi k. And then where does sine x equal negative 1? That actually only happens at 3 pi over 2, like in between quadrants 3 and 4. So x is equal to 3 pi over 2. And then again, I'll go ahead and bring back plus or minus 2 pi k. So for the first time today, we actually have 3 statements that together make up our solution set. So the pi over 6 and the 5 pi over 6 will make this factor equal to 0. And the 3 pi over 2 will make that factor equal to 0. So together, that is how we can solve the equation 1 plus sine x equals 2 cosine squared. The key to this problem was changing cosine squared into 1 minus sine squared. And again, I chose to do that because I saw sine x on the left side of the equation. And I had to get the equation to only be sines, even if they are sine squared and sine not squared. Okay, that's going to do it for this one. Thanks for watching.